Hello everyone and welcome back to another IGCSE Chemistry 0620 video. Today we'll be looking at electricity and electrochemistry, and which is unit 4 according to the IGCSE syllabus, and I'm also going to be following the order presented in the IGCSE syllabus. Um, Except for the first few minutes of this video, where we'll be discussing about conductors and also just some basics about electricity, conductors and electricity. Now, what is electricity? Electricity is just a stream of electrons, and the most common supply of electricity in circuits would be a DC source, usually a cell, and multiple cells form a battery. So this is a symbol for a cell. This is the positive terminal. This is the positive terminal and this is the negative terminal. And electrons flow from the negative terminal to the positive terminal, which is something that you should definitely keep in mind. Now, conductors are materials that easily allow electrons to pass through them. So we say that they conduct electricity, while insulators resist the flow of electrons. Or in other words, they are bad conductors or non-conductors. And you can find out, or you could carry out an experiment to check if a substance is a conductor or an insulator using a very simple circuit. So I've already drawn a cell here. Let's just use this to draw the circuit. I can have like a switch over here. I can have a switch here, and this is my solid. So if my material or if my solid is a conductor, then it's going to allow, I made a mistake, sorry. Right. If my material is a conductor, it's going to do two things. If I use a lamp over here and my material is a conductor with the switch closed, then the bulb will light up. If the bulb doesn't light up, then the solid is almost certainly an insulator. Alternatively, I can also use a voltmeter where, if I have a voltmeter placed in the circuit, then assuming that the solid is a conductor, the voltmeter will deflect, and if it isn't a conductor, then the voltmeter won't deflect. And this can be carried out with all solids. Now you can also conduct a similar experiment to check if a liquid or a solution is a conductor. So let me just quickly draw the diagram for that. Right. So as you can see here, the setup for this demonstration is also very similar. When the switch is closed, and if this liquid over here is a conductor, then the voltmeter will deflect. Or rather, I should say, if the liquid conducts electricity, the voltmeter will deflect. And if it doesn't conduct electricity, then the voltmeter won't deflect. And alternatively, as I explained before, you can also use a bulb for similar results. Now, in most situations, you're likely to see three results. Let me just write them down real quick. Right. So here are the three results that you're likely to see when you carry out the previously explained experiments. Number one, if your solid is a metal or a carbon or graphite, sorry, not carbon. Right, I've corrected the mistake, sorry about that. If your solid is a metal or graphite, then it conducts electricity. Why? Because all metals and graphite have free electrons, which can carry electrical charges. Molecular substances such as H2O, CO2, ethanol, petrol, etc. Won't conduct electricity regardless of what state of matter they are in. So as solids or solutions or even liquids, they aren't going to conduct electricity, hence they are insulators. Ionic compounds are a little quirky. So as solids, ionic compounds are non-conductors. So for example, NaCl as a solid crystalline structure or NaCl crystals are non-conductors. However, if you were to use the second setup, using a molten ionic compound, so NaCl in its liquid form, or liquid is not necessarily the most accurate term, so using NaCl in its molten form, as you can see on the left, or if you were to make a solution using an ionic compound, so dissolving NaCl in water, then that substance would conduct electricity. And with that, we did finish the first real part. One thing you should note here, and we will express this in a few minutes, but note down the reason that ionic compounds are able to conduct electricity in their molten or aqueous form is because when you put them, or when you melt them, or when you create a solution using an ionic compound, you're basically making it so that the ions are free to move. So similar to how metals have delocalized electrons, the ions in molten or aqueous ionic compounds are free to move and thus carry charges. Another thing, when you do conduct electricity, especially from a DC supply, through a molten or aqueous ionic compound, that ionic compound is likely to decompose, but we are going to discuss this more in a few minutes. So, yeah. Right. So over here, you'll notice that the term in red, electrolysis, has been highlighted. Electrolysis makes up the bulk of electrochemistry, and electrolysis, well, when it comes to defining electrolysis, even the definitions don't usually hold that much weight in terms of how many marks they give you. I would say there are four key things that you need to express through your answer in order to actually gain marks, especially when defining electrolysis. So number one, you should mention that it's a gradual decomposition, or you can say decay or breakdown, but decomposition is the most optimal and preferred term. So it's the gradual decomposition of an ionic compound in its molten or aqueous form. So mentioning ionic compounds and also mentioning the state in which the ionic compound is in is very important. And and the third point that you should mention is that it occurs when direct current is passed through it. That DC is just direct current. So it's the gradual decomposition of an ionic compound in its molten or aqueous form when direct current is passed through it. So the three things that I've written down here are the things that you should include in your answer. And the fourth point that I was talking about is just the coherency with which you write your answer. So just write what I said, basically. We'll also be looking at the definition of an electrolyte. Now I know this seems kind of weird. It will make sense what I'm talking about in a minute. So an electrolyte is just an ionic substance in its aqueous or molten form that can conduct electricity. So all aqueous solutions of acids, bases, and salts are electrolytes. So if I have a solution, so a few examples would be H2SO4. If I have it as an aqueous solution, this is an electrolyte. NaOH, sodium hydroxide, in its aqueous form, this is an electrolyte. If I have something like, let's say, magnesium oxide in its molten form, this is an electrolyte. Even urine, because urine is essentially a solution of multiple salts along with water and urea and other substances, but it's still composed of where it still contains free electrons. Which brings me to the most important thing that you should remember when talking about electrolytes. There are two conditions that a substance should meet in order to be considered an electrolyte. Number one, it must have ions, or it must have oppositely charged ions. There must be oppositely charged ions present. Oppositely charged ions present, and this is to say that an electrolyte must contain both cations and anions. From the examples, you can see that H2SO4 contains cations from the hydrogen ions, and also sulfate ions, which are the anions. The same can be said about sodium hydroxide, magnesium oxide, and all other electrolytes. This is the first condition. The second condition should be that the ions should be free to move. The ions should be free to move. Now, this condition is the reason why electrolytes are ionic compounds in their aqueous or molten form. For example, NaCl in its solid form has oppositely charged ions. So it has a sodium ion and it has a chloride ion, which are oppositely charged. However, as a solid, these ions aren't free to move, so they aren't able to carry electrical charges. It's only when I melt NaCl, or if I make a solution using NaCl, do the ions become free to move, and they need to be free to move to carry charges. And arguably, this second condition is the most important thing that you should keep in mind when talking about electrolytes. Now, electrodes are basically just conductors. Let me write this down. Electrodes. Electrodes are just solid conductors in the form of rods, plates, or wires by which electricity enters and leaves the electrolyte. And I'm realizing now that this sounds a little confusing without a diagram, so let me just draw one real quick. Right, so here's a diagram of an electrolytic cell. So this entire contraption is called an electrolytic cell, where electricity gives rise to a chemical reaction, and you'll see how in a few minutes. So the electrolyte is this substance right here, the electrolyte. It's either a molten ionic compound, or it's a solution of an ionic compound, hence it's liquid. These two rectangles here are the electrodes. There are always two electrodes, and they are solid conductors, which, as you can see, they are the reason that DC electricity from the DC source is able to leave and exit the electrolyte. Now, well, since we have the diagram here, it's going to be easy to describe electrolysis. But before I do that, I'm going to have to explain two things. Number one, I'm going to have to help you distinguish between the two electrodes, which is the first thing I'll do. And secondly, we'll discuss the ionic theory of electrolysis before looking at a few examples mentioned in the syllabus. Right. So over here, you can see that one of the electrodes is connected to the positive terminal of the battery, and this electrode is called the anode. So this is the anode. Sorry, it's the anode. The positive electrode is the anode, Pa. It's easy to remember, Pa, positive anode. The reason that now an anion is a negative ion, but an anode is a positive electrode, which can get confusing. But an easy way of remembering it is that an anode is an anion attracting electrode. And to attract something negative, you yourself need to be positive. Hence, the anode is the positive electrode. And you can also see that the electrode connected to the negative terminal is a cation attracting electrode, and to attract something positive, such as a cation, you yourself need to be negative. Hence, we call it a cathode. A cathode. So those are the two different names. That's how you distinguish between the two electrodes. Now that we know that, we can start talking about the ionic theory of electrolysis. Right. So the ionic theory of electrolysis it's just an explanation for what happens during electrolysis when direct current flows through an electrolyte. And it involves three steps. Number one, decomposition. So when you pass direct current through the electrolyte, it's going to decompose into its respective cations and anions. So for example, a molten electrolyte such as NaCl will decompose into its respective or its congruent ions. So it's going to form a sodium ion plus a chloride ion. Another example would be magnesium oxide. Again, let's take a molten electrolyte. It's going to decompose to form a magnesium ion and an oxide ion. Now, let's look at the decomposition of an aqueous ionic compound. If I were to ask you to to figure out how aqueous sodium chloride decomposes, most of you would draw something similar to this. That would be wrong, because remember, NaCl, a solution of a solution of sodium chloride is basically sodium chloride dissolved in water, and water is also going to take part in the decomposition because it's also composed of two different ions. What do I mean? Basically, when I say that, when I ask you to draw the decomposition of aqueous sodium chloride, I expect you to draw, this. I should see something like this: sodium ions plus chloride ions. And on top of that, I also expect to see the decomposition of water, which is as follows: a hydrogen ion plus an hydroxide ion. Right, so that's how water decomposes. You should definitely keep this in mind. For all aqueous solutions, you are going to show the decomposition of the actual ionic compound, and on top of that, you also must show the decomposition of water. That's for aqueous solutions of ionic compounds. If the electrolyte is molten, then that's easy, you don't need to worry about it. And the decomposition of water is always like this. The only thing that changes is this thing right here. This remains the same. So anyway, that's decomposition done. Now let's talk about migration. Basically, once the two separate ions have been formed, or the two oppositely charged ions have been formed, they migrate or move towards their respective electrodes. So the sodium ion will move to the cathode. So the cation will move to the cathode, and the anion, such as the chloride ion, will move to the anode. This is migration. The third step, or the third process that occurs, is discharge, where once the ions reach their respective electrodes, they discharge or they lose their charge to form products on the electrode. This will be easier to explain once we look at an example, so let's do that. Right, so the first example that we'll be looking at is the electrolysis of molten lead-2 bromide, and this is also the first it's the first thing that's in your syllabus, well, technically it's the third thing, but it's the first electrolyte whose electrolysis you should be familiar with. Notice how this is a molten electrolyte, so you don't need to worry about showing the decomposition of water. You'll notice that I changed the label to be PbBr2L. That's molten lead bromide. A few things to note. Number one, the symbol for lead is Pb. Number two, notice the state symbol L because it's a molten electrolyte. Number three, you should know how to come up with the formulae for substances by now. And number five, which I forgot to mention before, but you'll notice that the container here has been labeled as a voltmeter. That's just the name for the container. This entire contraption is called the electrolytic cell, and the container here is called a voltmeter. So that's just something I forgot to point out before. Now, during the electrolysis of lead 2 bromide, let's follow the steps. Number one, decomposition. Your lead bromide, again, it's a molten electrolyte, so don't worry about water for now. Br2L is going to decompose to form Pb plus 2. Well, that's my bad, just a second. Molten lead bromide will decompose to form a lead ion which has a plus 2 charge, and a bromide ion has a minus 1 charge. However, remember it needs to be balanced, so you'll put a 2 here. So plus 2 plus, well, if you do 2 times minus 1, that's minus 2. So minus 2 plus 2, they cancel out. And that's just a quick tip when it comes to balancing your ionic equations. Your decomposition things. The second thing, migration. So the lead ions migrate to the cathode, as in you're going to see the lead ions here, plus 2, plus 2, plus 2. Those are the lead ions going to the cathode, and you'll see the bromide ions at the anode. 1, 2, 3, 4, 5, 6. There'll be twice as many bromide ions than lead ions due to their ratio. Minus, well, you can just write minus, right. That's migration done. And discharge, where they lose their charge. Now, okay, let's just do it. Discharge. I like to start with discharge at the anode, and I'll explain why first. So discharge at the anode, you have the Br minus, the bromide ion, which will lose 1 electron to form bromine. Now, pro tip, remember bromine is a halogen, and all halogens are diatoms. So you have to put a 2 here. But if you put a 2 here, the rest of the equation is not balanced. So you just have to put a 2 here and a 2 here. And now it's balanced. This is called a half cell equation. Basically, an electrolytic cell is a complete cell in quotation marks. So if you write the equation or the ionic equation at only one of the electrodes, you're writing an equation for only half of the cell, which is why you call it a half cell equation. Now at the cathode, you have the lead ions, which is plus 2. They'll gain 2 electrons to form lead. Right, now there are 2 things that I want you to note here. Number 1, you'll notice that the electrons that are lost here are the ones that are gained here. You'll notice that they have the same coefficients if you ignore the signs. This is because of the law of conservation of mass, where you can't really lose matter, you can't destroy it, you can't create it. So essentially, the ions that the electrons that are lost by the ions at the anode, they travel up the circuit and eventually make their way through the cathode, where the where the lead ions gain the electrons. And yeah, that's a fundamental principle in electrolysis. And if you can wrap your head around that, then creating Hausdorff equations will be a breeze for you. The second thing that I wanted to mention is that, the electrons that are lost here are the ones that are gained here. So that's the first thing. Number two, and I mentioned this before, but the coefficients for the electrons must be equal, ignoring the sign, of course. One more thing. So I prefer to write my Hausdorff equation at the anode like this, like this. But the thing is, you can also write it it's still correct, and IGCSE should still mark you right for it, and the examiner will almost certainly mark you right. But there is a preference in the scientific community to not put a negative symbol for something that's already negative. So electrons are already negative. There's no point in putting a negative symbol in front of it. So alternatively, you can write the Hausdorff equation at the anode as bromide ion is equals to a bromine molecule plus 2 electrons. They are both correct, and either one will fetch you marks. The only reason I don't like the second one is because it gets confusing, especially when you have to balance the equations. And also, it just makes more sense to me to have a minus on one of them and a plus on the other one. But that's just a personal preference, and they're all correct at the end of the day. So with that, I think the ionic theory of electrolysis is clear, and we'll still be looking at some more examples, so don't worry. There are two things that I should mention. Number one, let's talk about the products that are formed. Because remember, once discharge occurs, products are formed. So the products at the anode, the product will be bromine gas, a reddish brown bromine gas. So you can write that. Bubbles of bromine gas. At the cathode, you are going to see a lead metal form. So it's basically going to coat the electrode. Metal. That's the products. Now let's look at the observations. There are like 4 or 5 things that I really have to say. Number one, the products and observations are not the same things. The products are the theoretical things that you know are going to form based on your Hausdorff equations and working out and things like that. Observations are just what you see. So, for example, at the anode, the observation will be bubbles of red-brown gas. So, because it's a gas that will be underwater. It's a gas, and you're going to see bubbles, and the gas will be reddish brown in color because that's the color of bromine. But you cannot write bromine because you don't know it's bromine just by looking at it. You need to chemically test it, or you need to work it out with knowledge beforehand in order to know that. At the cathode, the product will be silver metal, because again, you don't know that it's lead. You just know that it's silver in color and it's metal. So that's the difference between products and observations. The next thing that I have to mention is that during this electrolysis, we use something known as inert electrodes. Inert electrodes are electrodes that do not react with the electrolyte for obvious reasons. If they were to react, then you wouldn't be able to carry out electrolysis properly, and that would be a problem. So we use inert electrodes which are unreactive, or they don't react with the electrolyte. The two examples of inert electrodes that IGCSE requires you to know are that number one, graphite electrodes, which are the most commonly used. Graphite, alternatively, you can also say carbon, you'll still be marked correct, but graphite is more accurate. Graphite electrodes and platinum, which are still used, but the thing is, platinum is really expensive and is really rare, so graphite is more common. These are the two inert electrodes that you need to know. Right, and with that, I think we are done with the decomposition of molten lead to bromide. Next, we'll be looking at the decomposition of a concentrated aqueous sodium chloride solution. So that's going to be a little different. Okay, I lied before. There's one thing that I have to mention first. So we have the half cell equations, which, as I mentioned, it's half of the stuff that's happening in the cell, which is why you call it a half cell equation. You can get something called a full cell ionic equation, which is just a combination of the two equations with stars near them. What I mean is that you can write the half cell equations as two bromide ions combining with a lead ion to form a bromine molecule and lead. This is the full cell ionic equation, a full cell ionic equation, while the previous two that we wrote were half cell ionic equations. And now finally, I think we can talk about we can talk about some of the rules of preferential discharge, which you look at right now. Right, so when an aqueous solution of an ionic compound such as NaClAq decomposes, you basically, rather than having just two kinds of ions, you end up with four kinds of ions through the decomposition of the NaCl and also the decomposition of water. So to demonstrate that, you have Na plus, Cl minus, H plus, OH minus. So you have four different types of ions as opposed to just two different types. Now these two go to the cathode and these two go to the anode. And since two ions are going to each electrode, how do you figure out which one discharges and which one doesn't? There are a few rules to that, and we call this preferential discharge. So let's discuss those rules before we look at any examples of describing electrolysis for aqueous solutions. Right, so these are the rules for preferential discharge. The first rule applies only to cathodes. Now, the series that you see on the left, which is this one, is called the reactivity series, and as you go from top to bottom, the reactivity of metals decreases. However, if you were to flip this series on its head and change or flip it upside down and change all the metals to their respective ions, you would get something called the electrochemical series. And to find out which element discharges to find out whether a metal ion discharges at the cathode instead of the hydrogen ion, you would use the electrochemical series. Now, what does this mean? It means that any of the ions that are below the hydrogen ion in the electrochemical series will not discharge at the cathode. So in the case for my sodium chloride aqueous solution, because the sodium ion is below the hydrogen ion in the electrochemical series, it will not discharge, and instead you'll see the hydrogen ion discharge. So you'll have H plus 1 electron, which gives you hydrogen. Hydrogen is a diatom, so you account for that and balance accordingly. and this will be the half cell equation at the cathode. And obviously by proxy, any of these ions that are above the hydrogen ion are more reactive than it, which means that they have a stronger drive to gain electrons. And if you see any of these ions, then they'll discharge over hydrogen. Speaking strictly with the IGCSE syllabus, most commonly, if you see copper, you're most commonly going to see compounds that eventually decompose to give you the copper ion. It's very unlikely for you to see these guys. But yeah, that's just a general thing. Yeah, that's about it. That's the first rule. The second rule is right. So the first rule applied to the cathode specifically. The second rule applies only to the anode. Now we have some substances some solutions known as halides. Now a halide is any solution that contains a halogen, or it's a compound containing the ions of halogen. Now what does this mean? In the case for NaCl aqueous, chlorine is a halogen, so an aqueous solution of sodium chloride contains chloride ions, and so this is a halide. Another example of a halide was our previous example, lead bromide, that was Br2, lead bromide. This is also a halide. Another example that I can think of is potassium iodide, aqueous. So this is also a halide. Now, the main thing here is that if you have a solution, if the solution is a halide and it's concentrated, then the halide ion, it will be the one that discharges. But if it's diluted, then oxygen will form, or the hydroxide ion will discharge, forming oxygen. Now, if your solution is not a halide, then oxygen is going to discharge by proxy. The best thing to do here is to explain it via an example. Right, so I've drawn a bit of a spread to kind of summarize what I meant before. So the first question you need to ask is the solution a halide? If yes, then is it concentrated? If it is, then the ion for the halogen is the one that discharges. If it's a dilute halide solution, then the hydroxide ion discharges. And I'll be showing the discharge of a hydroxide ion soon. If the solution is not a halide, then the hydroxide ion will discharge. So now let's look at the discharge of a hydroxide ion. And this formula is going to be a constant. So anytime a hydroxide ion is to discharge during an electrolysis experiment, you're going to have to keep this equation as a constant and balance the other equation accordingly, if that makes sense. So 4OH minus 4 electrons gives you 2H2O. So that's 2 molecules of water plus O2, oxygen. I suggest that you really take note of this half cell equation, because again it's a constant. So this one will never change, assuming that the hydroxide ion is the one discharging. Yeah. So this is a constant. I know it looks unusual, and again you can take this minus 4 electrons and bring it to the other side to make it plus 4 electrons. That would also be correct. I just prefer having the minus electrons there, so that when I write the discharge for the cations, I have a plus and minus value with the same coefficients, which acts as a reassurance for me, especially during an exam. So let me just highlight this in red, and then we'll look at a few more examples. So that's the discharge of the hydroxide ion. Again, take note of it. And Okay, the third and final rule for preferential discharge, number 3, depends on the nature of the electrode. So if the electrode is inert, then you don't really need to worry about this. But if it's a reactive electrode, which we'll be looking at later on in the chapter, there are a few other rules that you need to worry about. So, but for now, just keep that in your head. I'll close up on this spread chart and the half-cell ionic equation for the discharge of the hydroxide ion, and you can take a screenshot if you want, and then let's start with a few more examples. Right, so this is the second example we'll be dealing with, the electrolysis of an aqueous solution of a concentrated aqueous solution of sodium chloride. So again, you'll notice that the setup is the same, and we'll be using inert electrodes like always, specifically graphite. You can use platinum as well, but usually graphite is more practical. Either way, it doesn't matter. An inert electrode. Notice how I changed the labeling for the electrolyte, and I just noticed that the ions are still there. Let me just remove those. Right. So the first thing that we should look at here is number 1, the decomposition. So the decomposition here, since it's an aqueous solution, remember you have to show both the ionic compound and water. So it decomposes as such. You end up with sodium ions plus chloride ions, and it's balanced. And you also need to show the decomposition of water. So H2O decomposes to give you a hydrogen ion and a hydroxide ion. Again, this is balanced. Now migration, I won't really write anything down, but since there's no point, okay, no, maybe I should write it down. Na plus and H plus, so these two go to the cathode, and then the chloride ions and the hydroxide ions go to the anode. I think that's self-explanatory and easy to understand. Now we get to the discharge, where we need to try and remember the rules of preferential discharge. So let's start with the anode. I prefer that. At the anode. So remember, these two go to the anode. So between these two, number 1, we need to identify, is this a halide solution? The answer is yes, due to the presence of the chloride ion. Number 2, is it concentrated or dilute? The question says that it's concentrated. And because it's concentrated, the chloride ion will discharge. So you have Cl minus electron, which gives you chlorine. It seems that it just started raining, so if you hear any background noise, please excuse me. I don't think it should be too bad. Again, chlorine, remember, it's a halogen. Halogens are diatoms, so you have to put a 2 here. And if you put a 2 here, then you have to balance the rest of the equation. So you just put a 2 everywhere else. Again, this minus 2 electrons, you can also write this half cell equation as 2 chloride ions, a chlorine molecule, and plus 2 electrons. And while this is preferred, they're both correct and they'll both be accepted by Cambridge. So anyway, that's the half cell equation at the anode. Let's look at what happens at the cathode. At the cathode. Now at the cathode, you have these two ions. You have these two ions going to the cathode, the sodium ion and the hydrogen ion. So you need to recall the rule for the cathode, where ions that are below the hydrogen ion on the electrochemical series will not be discharged. The sodium ion, right off the bat, is really far, it's below the hydrogen ion, so you will see the hydrogen ion discharging. So you have H plus 1 electron which gives you hydrogen. Remember, it's a diatom, so 2, 2, 2, and those are your half cell equations. So with this, we have the two half cell equations at in the electrolytic cell. Again, you can write a full cell equation by just combining them. So 2 chloride ions plus 2 ions, hydrogen ions will give you a chlorine molecule and a hydrogen molecule. That's the full cell equation. Now we also need to talk about the product. Remember, products and observations aren't the same thing. So for products at the anode, you're going to see bubbles of chlorine gas, while at the cathode, you're going to see bubbles of hydrogen gas. For observations, remember they are not the same. Again, I cannot stress this enough. And in most IGCSE questions, you're more likely to see observations than products, but you still need to know about both of them. In this case, the observation at the cathode will be bubbles of green gas. Again, you don't know that it's chlorine just by looking at it. The only reason you know that the gas is chlorine is through working it out or by having some prior knowledge about the experiment. At the cathode, the observation would be bubbles of colorless gas. And that's it for this example. One thing I'll point out, this was a concentrated solution. One thing that is common for the electrolysis of dilute solutions is that when a dilute solution decomposes, or when a dilute solution undergoes electrolysis, when it undergoes electrolysis, water always decomposes. That's just a common thing that occurs. Water decomposes when you carry out electrolysis with dilute solutions. So anyway, so with the chloride ions and the hydrogen ions discharging and then being formed as products, you're left with sodium ions. You're left with sodium ions and oxide ions, hydroxide ions in the solution, and these two combine to form to give a solution of sodium hydroxide. Once all of the electrolyzed products have been formed. And yeah, I think we are done with this second example. Right. The third example that the IGCSE syllabus requires you to know is the electrolysis of an aqueous solution of dilute sulfuric acid. Just a second, let me erase this. Right. So again, you just follow the normal steps. For the decomposition, since it's an aqueous solution, you need to show the decomposition of both the ionic compound and the ionic compound and water. So in this case, the sulfuric acid decomposes to form two hydrogen ions, and one sulfate ion. A sulfate ion has a -2 charge, if I recall correctly. And you also showed the decomposition of water, which again is a standard. So you have 2H plus. I'm sorry, it's just H plus OH minus. That's the decomposition done. For migration, you'll notice that at the cathode, only hydrogen ions will be there, because when it comes to the cations, in this case, the only cations are hydrogen ions. So all of these guys will go to the cathode, right? So you don't need to worry about preferential discharge there. And then you'll have the sulfate ion and the hydroxide ion go to the anode. So over here, you'll see preferential discharge occur. So let's do the discharge. Let's get the anode out of the way. At the anode, right? Uh, Now, your first question here is the solution a halide? In this case, it's not a halide. So automatically, the hydroxide ion will discharge. And remember, the discharge for a hydroxide ion has a standard formula. So 4 hydroxide ions will they will lose 4 electrons to form 2 molecules of water and oxygen. Again, you can write this ion on the other side, on the product side, as plus 4 electrons, but either way is correct. So this is the hard part is done. The discharge that occurs at the cathode is just the discharge of hydrogen cathode. So you have H plus plus 1 electron, which gives you hydrogen. Remember, hydrogen is a diatom, so you balance accordingly. And the second thing you need to remember is that this number and this number, or the coefficients, should be equal. They have to be the same, ignoring the symbol. This is because the the electrons that are lost here are the ones that are gained here. Hence, they must be equal. And to do that, you just multiply this entire thing by 2. So the final half cell equation at the cathode is 4H plus 4 electrons, giving you 2 molecules of hydrogen. And again, the full cell equation is just a combination of everything. So 4H plus 4 hydroxide ions gives you 2H2O plus 2H2 plus O2. You can confirm if everything is balanced. For hydrogen, for 8, for 8 hydrogen, 8 hydrogen as well. Then you have 4 oxygen. In total, you have 4 oxygen, and yeah, that's balanced. That's the full cell ionic equation done. Let's look at the products. The products are obviously bubbles of hydrogen and bubbles of oxygen at their respective electrodes. The observations, which are not the same as the products, you'll see colorless bubbles in both. That's the only observation you see. Colorless bubbles formed at both electrodes. Right. So now there's something called the Hofmann's voltameter. The Hofmann's voltameter. Again, recall that the container here is called a voltameter. So the Hofmann's voltameter, it's still relating to electrolysis. The Hofmann's voltameter is just a voltameter that's shaped like an H. It still helps you carry out electrolysis, but it's specifically used to carry out the electrolysis of acidified water, which is a fancy way of saying dilute acids. Dilute acids. So we've already looked at the electrolysis of dilute sulfuric acid using a normal electrolytic cell. So I'm now going to draw the Hofmann's voltameter and show, the electrolysis will be the same, but I'll just show the difference between a normal electrolytic cell and the Hofmann's voltameter. Right, as you can see, this is a Hofmann's voltameter. I still have the normal electrolytic cell at the top, and I have the Hofmann's voltameter here. Okay, so technically there should be another cylinder right here. Just a second. So this is the Hofmann's voltameter. As you can see, it has an H shape, or its shape reminisces that of an H. Right, so this is the Hofmann's voltmeter completed. Electricity will obviously travel from the negative terminal to the positive terminal, and the results will be the exact same. So at the positive terminal, you'll see water forming, you'll see oxygen that forms O2 gas, and at the negative terminal, or rather at the right hand side, you'll see hydrogen. Now, again, the results, and in terms of theory, or in terms of the ionic theory of electrolysis, everything remains the same. It's just that the shape of the voltmeter changes, and we use the Hofmann's voltmeter to deduce two things. Number one, it helps us deduce that water is composed of hydrogen and oxygen only. So water is hydrogen and oxygen only. That's the first deduction that we can make from the Hofmann's voltmeter, because remember, when a dilute solution electrolyzes, and in this case, when a dilute acid or acidified water undergoes electrolysis, water is the thing that decomposes. So that way, water is only hydrogen and oxygen. And number two, you can see that the thing for hydrogen is a lot larger than the thing for oxygen. And in fact, if I were to draw the scale, the length for hydrogen would be twice as long as oxygen. That's because the Hofmann's voltmeter helps us make the deduction that water is 2 parts hydrogen and 1 part oxygen, and through this we get the formula for water as H2O. So that's just the Hofmann's voltmeter. One thing that you should note here is that in the Hofmann's voltmeter, a standard practice, you use inert electrodes, but a standard practice is to use platinum electrodes. There's no special reason as to why, it's just a standard thing that's been developed in industries. And yeah, that's the Hofmann's voltmeter. Right, so far we've been using inert electrodes for all of our electrolysis demonstrations. But now the syllabus also requires you to know, it requires you to be able to compare the results between the electrolysis of, I would say, the electrolysis of a solution of copper 2 sulfate using both inert and reactive electrodes. And basically the setup is the exact same, and it's similar to what we've been using so far. The only difference is that the one on the left is making use of inert electrodes, and in this case I'm using graphite. You can also use platinum, of course, but graphite is fine. And in the right one, we are using reactive electrodes, in this case copper. So the electrodes are made up of copper. The electrolyte in both cases is aqueous solution of copper 2 sulfate. Whether it's dilute or concentrated in this scenario won't matter, because in either case you're going to get the same results. And the best, let's just start working it out. So let's do the one with inert electrodes first, since we're familiar with it. I'll be quick with this one. So this is the discharge. And because it's an aqueous solution, you have CuSO4, which discharges to form Cu plus 2 plus S, the sulfate ion, which is minus 2, it has a minus 2 charge. Again, this is an aqueous solution, so you must show the decomposition of water. H plus the hydroxide ion. As you can see, this is the discharge complete. Migration. So over here, basically, you're going to see the copper ions, so that's Cu plus 2, and the hydrogen ions going to the cathode, while the sulfate ions, which is CO4 minus 2, and the hydroxide ions will be going to the anode. That's just the migration, which we finished. The discharge. Let's start with the anode. So at the anode, at the anode, you have the sulfate ions and then you have the hydroxide ions. By the laws of preferential discharge, hydroxide ions will be the ones to discharge. So let's just be quick with it. You would get this. Remember, this is a standard, so 2H2O plus O2. And at the cathode, when it comes, copper ion is above the hydrogen ion, so it's going to discharge. You have Cu plus 2 electrons forming copper, right? And again, I want you to remember that these two have to have the same coefficients. So you just take this whole thing and multiply it by 2. So you end up with 2 copper ions plus 4 electrons, giving you 2 copper atoms. So this and this are the two half cell equations. You can obviously get the full cell equation from this. Let's look at what happens when we use reactive electrodes. So the previous one was something we are all familiar with by now. Let's just look at the reactive electrodes. At the cathode, the discharge will be the same. The decomposition will be the same. Oh, I seem to have made a mistake. It should say decomposition. Right, so let's be mindful of that. Decomposition. The decomposition here will be the exact same. It will be the same, so I'm not really going to write it down, and the migration will also be the same. So let's just look at what happens for the discharge. These two will be the same. The discharge in this case, we'll start with the cathode. So just hold on. Usually I like to start with the anode. Here, let's start with the cathode. You'll see why in a second. So at the cathode, again, so the copper ions will be the ones that discharge. So basically you'll have Cu plus 2 electrons forming copper, right? And this copper will be solid. And these ions are suspended in water, so they're aqueous. At the anode, you're going to see something different. So the anode here will actually involve, at the anode, which itself is made up of copper, you're basically going to see the reverse of this, in the sense that the copper anode is going to now lose 2 electrons, forming copper ions, Cu plus 2. So this is a solid and this is aqueous. And of course this copper comes from the copper anode or the electrode. And basically the result here is that the anode dissolves, and thus the copper ions that are formed move to the cathode to form the copper. So these ions move to the copper alongside the ones that were already decomposed. And so copper moves from anode to the cathode. Subsequently, the electrons that are lost here are the ones that are gained here. That's always a constant, remember. And now, arguably the most important thing that you need to take away, aside from the half-cell equations, is also the observations, because the observations for both of these are different. So my question here is that, what should I erase? Because I need to make space. Okay, just a second. Right, so these are the observations, or the comparative observations between the two different demonstrations. I think the observations for the inert electrodes are pretty self-explanatory, and they should be obvious by now. Aside from the last one, basically copper sulfate solution it has a bright blue color, but as the copper, after decomposition, as the copper ions become discharged, well, the blue color comes from the copper ions, right? So as the copper ions become discharged and form as metal, or form as copper metal on top of the carbon electrodes, the color of the solution becomes paler, and by proxy the cathode gets bigger. And obviously colorless bubbles form at the anode. When you use reactive electrodes, again the cathode gets bigger, as I explained before, and also the anode diminishes or dissolves, which I also explained. But the color of the solution remains the same because of the anode dissolving. Yeah, so those are the observations, and that's how reactive electrodes, or that's how electrolysis with reactive electrodes differ from that of inert electrodes. Right, so here we have electroplating. Electroplating means using electricity to coat one metal with another, and it's usually used to either make an object like a steel jug look more pretty for cosmetic reasons, or it can also be used to prevent corrosion. So if something is made out of iron, you can use electroplating to cover it with another metal, and that helps prevent rusting. In this example, let's use an example, in fact. So this is a steel jug, I guess, a steel jar, steel jug. Let's say you want to coat it with silver. So over here, our anode is made out of silver, so it's a reactive anode. Electroplating involves using reactive anodes. And our electrolyte needs to be a soluble compound that contains silver. So we can use something like silver nitrate, an aqueous solution of silver nitrate. Silver nitrate, that's aqueous. So let's just look at what happens in this scenario. Well, the decomposition will be pretty simple. You're going to, you don't really need to worry about the decomposition. But when electricity flows through the silver anode, what happens is that the anode will dissolve, similar to how the copper anode dissolved before. So this Ag, which is solid, will decompose, it will decompose to form the silver ion and an electron. And this is aqueous. And the silver, and this is at the anode. At the cathode, just a second. At the cathode, you have the silver ion, which gains an electron and forms argentinum or silver. So generally speaking, the thing that you want to electroplate, in this case a steel jug, will be in place of the cathode. So as you can see, usually the cathode will be here, but instead I've connected it to the steel jug. So it will be coated with it's going to be coated with silver, as explained by this second half-cell ionic equation. And as this occurs, you'll see this silver anode diminish or dissolve. Right. And also the electrolyte must be a solution. I mentioned this before, but the electrolyte must be a solution of a soluble compound containing X, in the sense that the anode is made up of X, where X is a reactive metal, and the electrolyte is a solution of a soluble compound of X. So in this case, silver nitrate. And that's how electroplating works. Let me just take a quick look at the syllabus. Right, the only thing that we need to tackle here is a hydrogen-oxygen fuel cell, which is pretty simple. So a hydrogen, you really don't need to get into the specifics of how it works, but a hydrogen-oxygen fuel cell basically uses hydrogen and oxygen to produce electricity, with water as the only chemical product. What does that mean? Let's look. Basically, when hydrogen and oxygen react, they produce water and thermal energy. Now, this is a normal reaction. You can, depending on how you carry it out, well, there's a specific cell that you can use called an electrochemical cell, where a chemical reaction gives rise to electricity, in order to make it so that the reaction is carried out like so. So hydrogen plus oxygen gives you water, and rather than producing only thermal energy, most of this energy is electrical energy. So it's just it's produced as a different form, and some of this energy does escape as heat energy. That's because of inefficiencies, and you can't really stop that. So some thermal energy. You don't need to get into the specifics of how this works, but this it's just the basic concept here. And I mentioned this before, but the hydrogen-oxygen fuel cell essentially uses hydrogen and oxygen to produce electricity, with water as the only chemical product. And water is harmless to the environment, which is why hydrogen-oxygen fuel cells are being developed as a potential alternative to petrol engines. You also need to be able to discuss the advantages and disadvantages of petrol engines. So I'll just be showing a table from a textbook, and it pretty much summarizes the advantages and disadvantages. Right. So in this table, I've summarized the advantages and disadvantages of the two kinds of engines respectively. There's nothing really to explain here. Just take a quick read, take a screenshot, save it. It's pretty self-explanatory. And yeah, with that, according to the syllabus, we are done with electrochemistry, from electrolysis to hydrogen-oxygen fuel cells. And yeah, that should be it. And with that, folks, we are done with another IGCSE chemistry video. We have officially completed Unit 4, which is electrochemistry. I hope, as always, I hope you at least learned something, but at the very least, you know how to go about your revisions and what to focus on. And yeah, thanks for watching. Maybe consider subscribing, and I'll see you on the next one.